Since the aviation disaster that claimed the lives of more than 250 people on the Air India flight occurred, investigators have proposed a series of explanations: simultaneous engine failure, incorrect cockpit handling, or even a terrorist plot. But none of these theories can explain why the Boeing 787 crashed just 52 seconds after takeoff. Everything fell into a dead end. Until a message was recovered from the burned phone of a passenger, only a single line, but it directly pointed to the real cause behind the entire catastrophe. So, what shocking truth did that passenger's message reveal? What additional clues did the investigators uncover from that line of text? Don't miss it. This video will expose the full truth. During the process of reviewing data for the investigation, Ahmedabad Police Chief Mr. G.S. Malik confirmed that more than 100 mobile phones had been collected from the crash site to examine for possible recordings or images that might shed light on the final moments. In parallel, the Boeing 787 has been reconstructed at a secured location where experts are conducting a full examination for technical failure, structural defects, or signs of an internal explosion. Everything was proceeding according to technical procedures until something was discovered. A text message emerged from the scorched data. It was a message from a passenger to a loved one in the final moments. No exact timestamp, no audio, no video. Just a few brief lines, but enough to shake the entire investigation team. "I just heard someone saying they were testing some system one last time. I don't know what it was. Then the plane shook hard during the takeoff. I want to come home to you." The words seemed ordinary, but they hinted at something irregular. Something went wrong, right before the aircraft left the ground. The phrase, "testing some system one last time," immediately became a focal point, forcing investigators to re-examine the entire startup procedure of the Boeing 787. And then, they discovered something no one could have anticipated: the very cause behind the entire catastrophe. The system check that the passenger accidentally overheard was actually a procedure to reboot the fuel monitoring system, a technical step allowed if the system is slow to respond or loses signal during pre-flight checks. The flight crew followed the procedure correctly. After the operation was completed, all indicators on the cockpit panel returned to normal status. No error displayed, no warning issued. However, what no one anticipated was that the monitoring software misinterpreted the aircraft's condition. Instead of confirming stability, the system mistakenly assessed a critical fault and automatically triggered an incorrect safety mode. Specifically, the system partially closed the electronic fuel valve, preventing adequate fuel supply to the engines. This is a protective mode designed to limit leaks or explosions if a technical risk is detected. But in this case, it was activated incorrectly and, more importantly, without any alert to the crew. From the cockpit, the pilots saw no sign of abnormality. The thrust indicators remained within safe limits. All performance gauges displayed normal values. The aircraft took off, began to climb. Everything appeared to be routine, until it reached an altitude of approximately 200 to 300 meters. At that exact moment, the engines began to lose thrust abruptly due to insufficient fuel. The crew was thrown into a completely passive situation. They had no idea that the fuel valve was not fully open. No one realized that the software had mistakenly activated the wrong safety mode. From the control panel, there was no sign of malfunction, no warning, no error message. And at such a low altitude, the pilots had no time to analyze the situation, nor did they have enough space to perform any emergency response procedures. From the moment thrust was lost to the moment the aircraft hit the ground, the entire sequence lasted less than 20 seconds. As the cause of thrust loss was gradually identified as insufficient fuel delivery, the focus of the investigation immediately shifted to the fuel valve control switch cluster, the component that serves as the intermediary between the cockpit and the electronic fuel supply system. A prominent hypothesis emerged: the signal from the fuel supply switch may not have reached the valve control system, or was delayed while the software was still in reboot mode, Under normal conditions, even a 1-second desynchronization between the switch and the control circuit could cause the valve to fail to open properly. Engineers believe this scenario is entirely possible if, during the system check, the software had not yet completed its confirmation sequence, while the cockpit display had already shown a ready state. This resulted in a false error. The system believed that fuel had been delivered, when in reality, the control circuit failed to send the open command to the mechanical actuator. The absence of any warning further intensified the danger. If the system itself is unaware of the interruption, the pilots would have no indicators to intervene. This is a form of technological blind spot, where everything appears operational on the surface, but internally, the system has already shut down. In that very context, the short message from the passenger, "I heard someone saying they were testing some system one last time," inadvertently became the missing piece to precisely reconstruct the moment the incident began. It confirmed a fact. The crew had performed a technical procedure right before takeoff, and the system reacted abnormally afterward. Currently, investigation teams from Boeing, GE, NTSB, and AAIB are conducting a full examination not only of the fuel valve and monitoring software, but also the physical switch cluster, signal transmission wires, intermediary processing circuits, and the startup panel. The goal is to determine whether there was a temporary disruption in the control signal flow or a software-hardware conflict that caused the valve to fail to open at the critical moment. Just when the cause seemed to be gradually clarified, the investigation did not come to a halt. On the contrary, it continued to reveal even more shocking details, indicating that the plane crash might be far more complex than any of the previous theories suggested. According to sources inside the AAIB, India's Aircraft Accident Investigation Bureau, authorities unexpectedly summoned a group of engineers who had previously worked on military drone development projects. This was an unprecedented move in the investigation of a civil aviation accident and raised a serious question. Could the aircraft have encountered a technological interference at a level beyond the scope of commercial systems? At the same time, a component located deep within the electronics bay, identified as a signal module from the auxiliary control cluster, was sealed and transferred for analysis to a military laboratory. Unlike other parts handled by the civilian technical team, this unit was given maximum protection and kept entirely separate from the black box analysis process. Leaked information suggests that this was the only intact component with potential to store data that had not been deleted or overwritten. Its handover to a military unit indicated a sensitivity level far beyond ordinary technical issues. More startlingly, the black box data showed a signal dropout lasting exactly 4 seconds, coinciding precisely with the moment the aircraft began to lose thrust. In aviation, such a recording gap is extremely rare and cannot be dismissed. It suggests that the flight data recording system was either paused or disabled due to a serious software failure, a system conflict, or external interference from an unidentified source. However, the most controversial finding came from the auxiliary positioning system, which is programmed to activate automatically during emergencies such as loss of thrust or loss of control. By design, this system should initiate immediately, yet the data indicated that it only started a few seconds after the loss of thrust, a delay compared to the technical specifications. Each new detail uncovered is shifting the entire direction of the investigation, and the deeper experts dig, the more they realize what happened on that doomed flight was no longer a simple accident. Although technical evidence has gradually revealed the sequence leading to the disaster, the biggest question remains unanswered. Why did both engines lose thrust almost simultaneously, with no warning from any system? This abnormal silence has made it impossible for the investigation to stop at software or procedural errors alone. As technical information became increasingly clear, a series of deeper and more controversial theories began to emerge, focusing on potential weaknesses in the design of the Boeing 787-8 itself. First hypothesis: flaws in the fuel system design. right after confirmation that both engines had ceased operation almost simultaneously. Public speculation surged. A recurring question was raised. Why did both sides lose thrust at the same time? And what caused the fuel system, supposedly built with multiple safety layers, to fail completely in just a few seconds? All suspicion turned toward the electronic fuel system on the Boeing 787-8. Unlike older aircraft that use simple mechanical electrical systems, the Boeing 787-8 relies on a fully software-controlled fuel structure. Fuel delivery to the two engines is managed by electronic modules, sensors, and coordination algorithms. This makes the aircraft more efficient, but also fully dependent on digital logic and signal accuracy. Previously, some internal aviation reports had warned, if the fuel system is restarted at the wrong time, or if there is a temporary signal loss between modules, the aircraft may experience fuel delivery confusion, causing one engine to shut down, or even both if the system fails to compensate. The core issue: the system does not operate each engine entirely independently. If the software misinterprets the aircraft's state, it could simultaneously command both fuel valves to close as a protective reflex, but triggered incorrectly. Many experts warn that the fuel system on the Boeing 787-8 is overly complex and sensitive. If it encounters a software conflict or signal mismatch, pilots may receive no warning, while the engines have already been cut off from fuel. An aerospace engineer stated, "Just one flaw in the control logic can cause the entire system to fall into error without anyone knowing, and by the time the engines lose thrust, it's already too late." This accident is forcing Boeing and investigators to reassess the entire fuel system design of the 787-8. Because if this theory proves true, the cause lies not just in human error or a software bug, but in a design philosophy that is too vulnerable to sudden failures. Second hypothesis: software update at the wrong time. A new investigative direction is drawing special attention: the possibility that a software update was implemented too close to the aircraft's scheduled departure, and that this alone may have caused the fuel system to misbehave. According to a former engineer who worked with Boeing's technical teams in Asia, there have been instances where patch updates were installed just hours before takeoff, intended to fix rare signal glitches in the 787 series. In the case of AI-171, system records show that the fuel monitoring software appeared to have been recently refreshed, while the aircraft was still on the ground. This update was not a procedural violation, but it was applied within a time window so narrow that no post-installation integration test could be performed. As the system rebooted shortly after, some of the default configurations had not yet fully synchronized, causing the fuel valve to receive only partial open commands instead of full authorization. Experts warn that software updates, if not tested in real operational environments, can cause temporary logic conflicts between control modules. In aviation, even a millisecond delay between a command and its physical execution can be catastrophic. The reality was, no warnings were triggered. No one in the cockpit knew that the version of the software they were flying with had not undergone full post-update validation. And if the update was performed by a local technician team without oversight from the manufacturer, the risk of misalignment would be even higher. This raises a critical question: who authorized the last-minute update, and why was it applied without standard verification protocols? If this theory proves correct, then the tragedy of AI-171 wasn't born of pilot error or faulty hardware, but of a blind trust in untested technology deployed too soon. Authorities have not ruled out the scenario that a fault was deliberately planted before takeoff, or that some technical manipulation occurred within the maintenance crew, flight team, or ground control. This theory closely resembles the MH370 case, where a meticulously planned scenario left no warning but was still capable of sending the entire control system into an unrecoverable state. In this context, if a flawed logic was pre-programmed into the fuel monitoring system, such as a condition preventing valve activation, then the system check would merely act as a trigger for a scenario calculated in advance. Although no solid evidence has been confirmed, AAIB and the Counterintelligence Unit of India's Ministry of Home Affairs are reportedly conducting a parallel investigation into this possibility. Meanwhile, another expert group is focusing on a quiet yet dangerous possibility: signal conflict between electronic devices within the aircraft. The Boeing 787-8 is fully operated by a fly-by-wire system. All control commands are transmitted via digital signals and intermediary software. This makes the aircraft extremely sensitive to potential interference from devices such as mobile phones, Wi-Fi transmitters, onboard entertainment systems, or even ground-based auto updates. Some experts suspect that a supporting software like in-flight Wi-Fi, entertainment signals, or automated updates may have conflicted with the fuel control module, causing the system to misinterpret aircraft status or send incorrect commands to the fuel valves. The problem is if such a fault occurs at the source code level or within the embedded processor. It would leave no clear trace or alert in the black box and could only be discovered through hardware-level analysis of each individual module. This is also why certain components have been sealed and transferred to military laboratories, the only facilities capable of decoding circuitry and tracing system behavior down to the microcontroller level. While a series of technical theories are being explored and the investigation expands in multiple directions, the most puzzling element comes from the responses, or lack thereof, from the parties directly involved. Air India, the operator of Flight AI-171, has remained completely silent on questions regarding the list of technical personnel present when the aircraft doors were closed, as well as any technology trials that may have occurred during the short maintenance window before departure. Several specific inquiries from the press and independent aviation safety organizations concerning maintenance records, software update devices, and final technical adjustments have received no response. Even basic information, such as the exact moment the fuel monitoring system was rebooted, has neither been confirmed nor denied. Boeing, meanwhile, has declined to comment on the auxiliary control software reportedly installed specifically for the 787-8 assigned to AI-171. According to multiple industry sources, aircraft delivered by Boeing to state-owned airlines sometimes include customized software configurations to meet specialized needs in navigation, security integration, or compatibility with local infrastructure. Boeing's refusal to acknowledge this has only intensified suspicions. Did the AI-171 contain a different code base? And if so, could it have contributed to the system malfunction? The situation became even more questionable when the U.S. National Transportation Safety Board, NTSB, which typically maintains a physical presence at crash sites involving American-made aircraft, abruptly withdrew its investigation team, opting instead for remote coordination with Indian authorities. No explanation was publicly provided, but many experts have interpreted this move as a potential sign of political containment of technical information. Meanwhile, several critical data sets, including the flight control software source code, fuel system logs, and emergency response algorithms, remain classified. No disclosure, no access granted to independent investigators. All of this has led the public to ask a deeper question: is something being hidden? And if that is true, then the tragedy of Flight AI-171 may not be a simple technical accident after all. But the consequences of Flight AI-171 did not stop at the number of fatalities. The crash quickly triggered a chain reaction, shaking India's entire civil aviation system and placing Boeing at the center of global scrutiny. Air India was forced to suspend more than 50 international flights, most of which used the Boeing 787 aircraft. The airline is now reviewing its entire operating schedule, maintenance procedures, and especially the fleets using the 787-8, after large numbers of passengers canceled bookings due to safety concerns. India's Ministry of Transport immediately ordered a comprehensive inspection of the entire fleet, aircraft startup procedures, the list of technicians involved in pre-flight maintenance, and the operation of fuel systems on all wide-body aircraft. The review was launched nationwide under tight supervision from the military and civil aviation security forces. Meanwhile, Boeing is facing an unprecedented media storm, considered the most intense since the 737 MAX crisis. Although the Dreamliner 787-8 has previously encountered multiple technical failures, including electrical faults, control software issues, and even circuit board fires, this is the first fatal crash linked directly to the model. Many airlines around the world, particularly in Asia and the Middle East, have requested that Boeing issue an urgent software update for their 787 fleets, and have paused any plans to expand operations with the 787-8 until the official investigation concludes. Experts believe the AI-171 disaster is not just an isolated incident, but could trigger a fundamental shift in how flight control systems are designed and how the aviation industry approaches integrated software technologies, once seen as a triumph of innovation, now exposed as a critical vulnerability. Just one brief message from a passenger, seemingly a personal farewell, unintentionally unlocked a chain of buried truths hidden beneath layers of supposedly flawless technology. From the system retest action to logic errors in the fuel monitoring software, from sudden thrust loss to the unresponsive navigation system, from mounting technical suspicions to the puzzling silence of involved parties, the AI-171 crash is no longer a mere operational failure, but a stark warning to the entire global aviation industry. A state-of-the-art aircraft, operated by an experienced crew, can still plunge to the ground in under 60 seconds simply because of a chain of undetected faults, no response protocols, and no system capable of raising an alarm in time. As aviation becomes increasingly software-dependent, the real question is no longer who failed, but rather, is the system misinterpreting what we believe is safe? And without that one message, perhaps we would never have known what truly happened. If you found this video valuable, don't forget to like and subscribe to follow our upcoming analyses. Feel free to share your thoughts in the comments section. Thank you for watching. And remember, what we share here is for reference and analysis only. Please combine it with other sources for a fuller and more objective perspective.